Hey guys, Saturday, going to be answering some questions from 5.3, as well as going through Descartes' rule of sign. We'll do that first, actually, and then do the question from 5.3 at the very end, just to kind of showcase all the different ways you can approach these problems. Let's get started. First off, I want to remind us where we ended last time. Last time we were talking about finding zeros of a function. And if you think back to last time, one of the main ways we had to do this was we looked at varying ways to use things like, finding the possible ones that could exist using the fundamental theorem of algebra, and then just brute force testing them over and over and over again. Testing, sometimes a dozen different values to try to find when we actually got a remainder of zero and therefore found a factor. It was a pain, right? Like, I can pull up my notes from last time. My notes, this huge stack of papers, it was awful. I mean, for one problem that we did last time, like, these were the steps we had to do. Like, it was ridiculous. It took forever. And it was because we ended up with all these possible zeros. Like, this big list was just a blast to find, let me tell you. Today we're going to talk about one of the ways you can kind of shorten that list and use some extra information to help you get a little faster with this stuff, so you're not trying to hurt your head so much trying to get through all these different things. So today we're going to talk about Descartes' rule of signs. Descartes was a famous mathematician. He's famous for developing the Cartesian coordinate system, which is how we graph things. That was his idea. So if you hate graphing, curse this guy, okay? Rene Descartes. Descartes' rule of signs is a concept that states that you can perform a very simple test to determine the positive and negative possible solutions. So, as a reminder from last time, we learned through one of our theorems that the degree indicates the number of solutions. So if you have a degree of 3, then there's going to be 3 solutions. If you have a degree of 4, there's going to be 4 solutions. If you have a degree of 5, there should be 5 solutions. Now, this includes multiplicity. It just does. Because if there's duplicates, they're included in that total. So it may be degree 3, but all 3 of them are the same. But that's still 3 solutions. It's just some of them are the same solution. And so that was what we talked about last time, was there's a cap on how many solutions that there could be. But we also talked about last time how we can use P over Q to determine possible solutions. This ended up being a huge list. For some problems that you have in your homework, like, there can be up to 20 different possible solutions. And those were the ones in the evens, especially that I was looking at. There were some that were just awful. But these are all possible solutions. Now, of course, not all of them are going to work. Because, again, if there's, only 3 solutions, but you have possible 40 of them, well, then it can be a pain to try to figure out which one's the right one. And as we saw that last time, we used a lot of synthetic division to test this. Right? We determined the degree, determined the number of solutions, we found the possible solutions, and then we just repeatedly used synthetic division, brute force, over and over again to test which of these actually works. Well, today, Descartes' rule of sign is going to give us a faster way to do this. A way to kind of guide us in the right direction and help us to choose ones that are better. So Descartes' rule of sign. Descartes' rule of sign. Okay, there's 2 different versions of this. For positive solutions, there's a way to find the answer. And for negative solutions. For positives, what you need to do is you need to count the sign changes on f of x. For the negatives, you need to count the sign changes on f of negative x. Now, let's look at a function, and I'll leave the example in the book to showcase this. but afterwards I will do want to make sure to get their pieces together and kind of see how all these things can fit. But let's go to some homework problems. Okay. So on these ones, let's look at 46. We'll do 46 and 48 here in a moment. So 46 states we have x cubed minus 1. So this is our f of x. Now the question becomes two parts. One, if I know what f of x is, what's f of negative x? So this is the first thing I should find. So step one, we need to do Descartes rule of sign. Make sure you know what f of x is, and make sure you know what f of negative x is. You can't perform the test unless you have those two things. So make sure you find these two things. Typically, one of these is given, and the other one has to be found manually. Now, if I'm given the first one, to find the second one, all I have to do is everywhere there used to be an x, I need to replace with negative x. So everywhere there used to be an x, I replace with negative x. And now what we want to do is we want to count the possible solutions that exist. So for this first one, notice that we have a positive x cubed and a negative 1, which means in total we have one sign change. Now, according to Descartes' rule of signs, however many sign changes there are, that's how many positive solutions there are. This is how it works. You just count the sign changes. So it changes from positive to negative. There is one change. Since there's one sign change, that indicates there should be one positive possible solution. If I go down here, usually when you do this one, you'll have to do some simplification. So whenever you do the f of negative x, make sure to simplify. Big detail. Always simplify that one. And then just count the changes. So let's ask ourselves, what happens here? We'll have negative x cubed. Well, let's split this into two parts. The negative sign. If it's a negative sign, this is equivalent to negative 1 cubed times x cubed. Well, x cubed is just x cubed. Negative 1 cubed just means negative 1 times negative 1 times negative 1. Negative 1 cubed is negative. Which means that this is my f of negative x. Notice that for this problem, the signs do not change. Sorry, my neighbor's pounding on some stuff he's working on. The signs do not change. Since there are no changes, this tells me there are 0 possible negative solutions. What that means is, if I want to determine, how many solutions there are, I shouldn't even guess a negative answer, because there are 0 possible. If there are 0 possible, that means that if I was to use things like P over Q and get a list of possible answers, all the ones that are negative, I can probably ignore, because there are 0 possible ones. There are 0 sign changes, so there are 0 possible negatives. Notice that the possible positive come from f of positive x. The possible negative come from f of negative x. And so this tells me that there are 1 positive possible solutions and 0 possible negative solutions. To illustrate this, in your text, you'll notice that it asks you to do a graphing problem. So it says to test it first, which is what I did. I got it boxed. That part of the answer is done. Then it wants to graph to confirm which of those possibilities is the actual combination. So now I'm going to pull up Desmos. And in Desmos, I'm going to look at x to the third minus 1. And look at that. How many negative solutions are there? None. How many positive solutions are there? 1. There are 0 negative solutions. There is 1 positive solutions. Now, a big key phrase here is the word possible, because it's possible that 2 things can happen with Descartes' rule of signs. Step 3. It's possible you have multiplicity. It is possible to have multiplicity, meaning that, and as actually happens in this case, there are no multiplicities, but it's possible there are. And then next, it's possible there are complex solutions. Descartes' rule of sign will not tell you either one of these situations. It just won't. And so it'll tell you the possible ones because it does not account for multiplicity. So it does not count multiplicity. Meaning I could end up with a higher number than I should. For this one, it does not count complex. It doesn't count it. So in this problem, just to reiterate some previous things, if I look at the degree, I should have 3 solutions. But notice, I only found 1. So where'd the other 2 go? Well, it turns out the other 2, we talked in a previous chapter about this, the other 2 are imaginary. And so this ends up being the solution. And let's showcase kind of how the textbook does this. So in your textbook, this example, I'll go back to it now. It starts by counting the sign changes. There's a single sign change. So we have negative to negative. That's not a sign change. We have negative to positive. So this counts as 1. We have positive negative. This counts as 2. And then negative to negative. So in the original, you notice it says listed 2 positive real solutions. When it's negative, it also had 2, just in different places. But that's okay. All we're doing is counting them. So it had 2 negative ones. So it's possible that 2 of them are positive, 2 of them are negative, meaning you have a total of 4, which is expected because it's a power of 4. However, it is also possible that some of these solutions could be complex. And notice how what it does is it lists the possible solutions as either groups of 2s. This is because, one of the theorems we did not talk about last time, but is important here, the linear factorization theorem states that you never get a single complex answer. They always come in pairs, right? If there's A plus BI, there's A minus BI. They always come in pairs, meaning there's either 0 complex solutions, or there's 2 complex solutions, or there's 4 complex solutions. They will only ever come in pairs. And so to find out the possible answers here, there are either 2 positive zeros, or those 2 are actually complex. There are either 2 negative zeros, or those 2 are complex. Or it's possible that all 4 of them are complex. But this table here illustrates just the different possibilities for what could be happening. But notice how this gives us a guide to figure out how to get the solutions. If you're testing out values and you find 2 positive real ones, then you should stop testing positive ones. They're not going to work. You should start testing negatives. Those are the only ones left that could possibly work. Same with the negatives. On a problem like this one, if you were trying to figure out the zeros to this original problem, and you found 2 negative ones that work, then you need to just stop. Stop testing negatives, because there's no more possible. The rest have to be positives. And so this is one of those ways that you can find your solutions just a little bit faster. Okay, let's look at 48 now. And we'll go through the same process here. I'm going to save myself some paper here and go ahead and do 48. Scrolling down, and I might even do 52 just to get you another one to practice on. Okay, 48. We have f of x equals, and we have x cubed minus 2x squared minus 5x plus 6. Now, first thing I'm going to do, I'm going to find f of negative x, right? That's the first thing I said to do, is whenever we're doing these kinds of problems, make sure you have f of x and you have f of negative x. Find those first, and make sure to simplify the f of negative x. There's a trick to simplifying that's really helpful, and I'll show it here. When we do the f of negative x cubed minus 2 negative x squared minus 5 negative x plus 6. The trick here is odd powers flip signs. That's one of the best ways to simplify this, okay? Is the odd powers will flip. Evens aren't going to do a thing, and there's a good reason why. Let's take a look. We already did one with x cubed, so we know this is going to become negative x cubed. However, the minus 2 and the negative x squared, so negative x squared would be negative x times negative x. Negative times a negative would make this positive, but then times negative 2 would keep this a negative 2. X times x would give me, of course, x squared. So you notice that the even terms stayed the same, whereas the odd term changed. If I keep going, you see the same thing happens. Negative 5 times negative x, negative times a negative is going to make this positive. 5 times x is going to be 5x. So notice again, the odd term changed from positive 5 to negative 5. And the 6, of course, just as a 6. So, here's the cool thing. One of the cheats on Descartes' rule of signs is odd powers flip, evens stay. And it's just one of those that comes from a little bit of practice. You'll see it and you'll know that you can just shortcut some of this step. Okay, well, let's start counting. All right, so how many sign changes we got? Remember, we got to do it once each. So the first one, we have positive x cubed. It becomes negative 2, so that's one change. Then we have a negative, that didn't change. Then we have negative to positive, so that's 2 changes. This one, we have negative to negative, that didn't change. Negative to positive, that's 1 change. And then we have positive to positive, so there's no changes. So there's 1 change here, and 1 change here. There's 1 change there. I apologize, it's getting kind of sloppy here, but make sure you watch it in order, and you'll know where all these colors came from. So this tells me there are either 2 positive answers, or because of the complex, there could be 0 positive answers. Remember, because complex comes in pairs, and so we got to account for complex. This is the very last step. You got to account for the complex answers. So it could be 2 positives, or those 2 could both be complex, meaning there could be 0 positives. The 1 just means there's 1 negative. If I had 2 complex negative solutions, they would end up not working. You can't have a pair with only 1. This is, think like, poker or any other card game. You can't have a pair if you got 1 card, right? But you could have a pair that are complex, thereby making this 2 become a 0. And so this is the list of the possible solutions. Just like before, I am going to graph this function using Desmos and see what I get. So here's Desmos. I'm going to graph the function. The function is x to the third minus 2x to the second minus 5x plus 6. And look at that. It happened to be that this was the answer. There happened to be 2 positive. There happened to be 1 negative. And again, just to see that, there's 1 negative, 2 positive. But it was equally likely that there could have been 0 positive and 1 negative. And so this can help to limit exactly what ones I want to test when I'm doing my other types of problems, like 22 from last time. Like, if I test this and I find a negative answer, then don't test anymore. No matter how nice they are or nasty they are, there ain't going to be more. You got one answer, and there it is. Okay? With the other one, like if you find one, then you know there's going to be another one, because there has to be 2 or 0. Those are the only possibilities. So if you find one positive answer, there's got to be a second somewhere. So find it. Descartes' rule of sign allows you to do these kinds of problems and get the result faster and easier if you use it. If you don't, well, then it's just a waste of time. So it's 46 and 48, back to back. Boom, boom. Let's look at 50, and then I'll deal with the question that was asked from a student. So from number 50. We have f of x is equal to x to the fourth plus 2x cubed minus 12x squared plus 14x minus 5. Okay, let's make it my first goal to find f of negative x. Well, everywhere there's an x, I replace with a negative x, so I would do negative x to the fourth plus 2 negative x cubed minus 12 negative x squared plus 14 negative x minus 5. And rather than trying to do the math, this time I'm just going to use those shortcuts we mentioned. Those shortcuts were even powers are going to stay, odd powers are going to flip signs. So let's take a look. So x to the fourth is an even power. It's going to stay x to the fourth. 2x to the third is an odd power, so we have negative 2x to the third. Negative 12x squared, the square is an even power, so it's going to stay. Plus 14x is going to change. Minus 5, minus 5. Okay, let's count those sign changes. Okay, so here, positive, positive, no change. Positive to negative, there's one change. Negative to positive, there's one change. Positive to negative, there's one change, which means there are 3 sign changes, which tells me there are either 3 or 1 positive solutions. Remember, there's either 3 positive or 2 of them are complex, meaning there's only 1 positive. For this one, positive to negative, there's 1. Then we have negative to negative, there's no change. Negative to negative, no change. Negative, negative, no change. So we have 1 sign change, which means there's 1 negative solution. And so again, we can use this to help indicate that there is a possibility of finding our solutions a little faster, because we can limit how we test. If I find 1 positive solution, that does not mean I'm finished. Maybe there's another one. If I find 1 negative solution, then I need to stop, because that's the only negative solution there's going to be. And so this can help eliminate that big long list. Because again, I cannot reinforce this thought enough, because until you do it a few times and realize just how much you're going to hate it, like, look at 22 again. Like, do you really want to sit there and test every one of these? And if your answer is, heck no, well then stuff like Descartes' rule of sign means that once I saw that negative 3 was going to work, I can just stop testing all those negative answers. All the ones that came after that were negative were useless, because it turns out if you apply Descartes' rule of sign to this problem, only 1 negative solution exists. And so once I got that one, I could have never bothered. I would have skipped like half a dozen problems. And when one problem is this dense, you have to look for better ways. And Descartes' rule of signs is one of those. So that is it for the section 5.5. If that's all you needed, you can go ahead and stop right here. But now I'm going to answer one of the questions we had from our homework. The question that I had was actually from section 5.3, and that was number 61. So let's go ahead and answer that question, and then I'm done for the day. Yay! So, homework question. It was from section 5.3, and it was number 61. This was 5.3 part 2. Let me go ahead and go to 5.3. Number 61. There we go. Okay. All right. It states, we have a polynomial of degree 5. What that tells me is we're going to have x to the 5th power in this problem, somehow, some way. Next, it tells me we have a double zero at x equals 1. What that tells me is if x equals 1 is a 0, that tells me that x minus 1 is a factor. And because it is a double zero, that means there's 2 of them. So that's how we read the first part of this problem. It says double zero at x equals 1. That means x minus 1 is a factor. Because it is a double zero, it means x minus 1 squared. Now, the second thing it tells me was that. The third thing was it has a triple zero. It's starting to sound like Words with Friends here, or Scrabble. Triple zero at x equals 3. Well, what does this mean? Well, this means that if x equals 3, that means we have x minus 3 as a factor, and it's tripled, so that means there are 3 of them. So, if I want to actually write out my solution, I would do x minus 1 squared and x minus 3 cubed. Now, there's one last detail that it tells me in the problem. And this is a big thing that I don't think I emphasized enough, and I'm glad somebody asked about this. It says it passes through the point 215. Here's the thing. This is one version of f of x, and it meets all the criteria that have been listed so far. It would have a power of 5, because you'd have x squared and x cubed for a total of 5 x's. It'd be x to the 5th. It does have a double zero at 1. It does have a triple zero at 3. But another answer also exists, right? 2 times the exact same thing. Like, this one also meets all of those qualifications, right? It still would have degree 5. It still has a double zero at 1. This is a triple zero at 3. So this one also meets the qualifications. So does this one. It also has a double zero at 1. It also has a triple zero at 3. It would also be degree 5. But these are different answers. If you were to graph these are different. So there's one last thing that's going to be in this f of x, the unknown a. Is there a number that should go out front that is different than 1? And how do we find that answer is the bigger one. So let me showcase how that's done. Ready? We do, to find the a, what we're going to do is we're going to plug in 2 and 15 into x and y. So, remember, your y is equivalent to f of x. What this means is 15 goes here. A is still there. And everywhere there's an x, we need to replace with 2. So, this function by itself is a possible answer, but we just don't know what a is. So how do we find a? Well, we use what they gave us. Remember, what they gave us is an x value and a y value, or if you prefer, an x and an f of x. So what do? Well, we just plug those things into what we do know. Like, we know this is an answer, So why not let x equal 2 and let y equal 15 and see what the other thing could be? So that's what we're going to do. Everywhere there used to be f of x, we put in 15 because we know that's the result. Everywhere there used to be an x, we put in 2 because we knew that used to be the result. And so this gives us a new equation where I can get a by itself. So let's do this. 2 minus 1 is 1. 2 minus 3 is negative 1. All right, 15 equals, okay, 1 squared is 1, and a times 1 is just a. Negative 1 cubed is negative 1, and negative 1 times a would be negative a. And then we divide to get a by itself. 15 divided by negative 1 would be negative 15 equals a. And now what I can do is I can take this equation. Everywhere there used to be an a, I can replace with negative 15 and get the answer f of x is equal to negative 15 x minus 1 squared x minus 3 cubed. And that is my final answer. If you stopped right here, you'd have met all requirements except one. And let me illustrate what that looks like. Here's Desmos again. My old equation was x minus 1 squared times x minus 3 cubed, right? That's the equation. But you'll notice that at 2, my answer isn't 15. At 2, my answer is like negative 1. So we know this answer is wrong. It has to be, because according to what it says in our problem, it's supposed to go through 2, 15, not 2, negative 1. So we know something's wrong here. So how do we fix it? Well, we substituted in to find out what that missing a was. If you forget this step, you'll get these three things to all be true. What you won't get is the right equation. Yes, this equation right here, it meets the criteria. X minus 1 twice. That tells me we're going to have a double zero at 1. X minus 3 cubed. That tells me we're going to have a triple zero at 3. But we did not get this one. And so we have to make sure this is the last step you do on questions like 61. And of course, the other ones in the same section, 63 and 65. Like, you have to make sure it actually goes to that point if it gives you a point. So like here, on 59, they gave you an intercept at 0, 9. You have to make sure to put that back in and get that answer. Okay, this is it. Getting here should be pretty standard. Getting this last step takes a little bit more effort, but once you got it, you just got to plug it back in and you're done. Make sure you take this step to figure out what A should be. And how do we do that? Well, we just plugged in 2 and 15, which were the two things they gave us from the very beginning. They gave us 2 and 15. Everywhere there was an x, we replaced with 2. Everywhere there was an f and x, we replaced with 15. And then we just solve like normal. That'll be it. A few minutes to do that. And there we go. I hope this helps. Make sure you get your homework turned in. Remember, the most recent section, including Descartes' rule of sign, is going to be due on Tuesday because it's such a long section. And we'll have our next assignment on Tuesday as well. We're more than halfway through the chapter, if you want to think about that. So let's go ahead and keep going. And I look forward to seeing you guys. If you have any more questions, let me know. I'll try to answer those as quickly as I can. But otherwise, I will see you guys on Tuesday.